This is the Mastering Spark Slack channel. So if you guys are doing your homeworks and it's getting exciting and, yeah, I don't know how to make this bigger. We can invite you guys to this. So we're trying to go farther. Some of us are trying to prepare talks for Apache Spark Summit in London. Very ambitious. But it just starts with simple steps, right? So if you want to be part of it, let me know. And Mariama might know this is started by Andrew. So Andrew is the main author, one of the 4 authors of the Mastering Spark book. And this is where Dylan just snoozed off. So we've been having a lot of intense discussions for the last 24 hours. And he says run the map matching stuff end to end. Haven't had the chance to look at the GraphX stuff. So let's see if stuff works. If it doesn't work, we'll just focus on the concepts and we'll figure out the versioning issues later. Okay, like maybe by next weekend or something. Before, like, say, half of you have handed in your 2 assignments. Okay, but it doesn't matter. The concepts should be enough, even if the notebooks are busted for now. So let's see what's there. So is my sound okay, Don? I don't know. I guess it's okay. So here is the contents for now. And I'm going to basically just bundle this and give it to you guys, I guess, as is. So it's not in any particular order. This is the stuff we did this morning. I will simply mention about this while you guys are looking at. I think this looks okay. So I'll rename this to Flow 31A, and I'll just dump this for you guys, and so you can. And oh well. So let's see. So export DVC archive to so this is kind of what I usually do early in the morning. So I'm going to call, it's already called 2 of 2. So I'll just drop it and commit and push. And then you can see it in the usual place in a minute. I have no idea where I am. Git Scalable Data Science, DBC Archives 2018. Right. I don't know what it's called. Is it 2 of 703 minus 2 of 2? So okay, so just give it a minute and then you'll see it there. So while that's happening, let me tell you highly recommended assignment. It's not assignment, it's exercise, homework. So this is again how I kind of keep up with a lot of changes that are happening. It's just too much going on. I like this bright talk thing. Sometimes you get really crappy talks, but sometimes you get really good talks. And eventually you will get really good talks all the time. So you have to sign up for this. But that's where I sort of, just have coffee and relax and watch some talks. And that's usually where I sort of start scanning what's interesting, right? So this one was actually one of the Bright talks, so you can watch the full talk. And he was using graph frames in Python. And so a lot of the concepts are explained nicely. And it has much more interesting D3 visualization with airports, for example. So this is quite interesting for you to build in. So, if you have geospatial information, then you can use maps and throw things on top. I won't go into it, but really knock yourself out. These are much more typical queries you would do in a so-called business intelligence setting, right? This is basically big data-based business intelligence. So you're trying to find out, what flights are delayed and, given various conditions. So this is so it's like a big, much more interesting graph than the tiny little graph we were playing with for just syntax. So I highly recommend going through this to properly understand things in a more real-world setting. Yeah. So we also use page ranks. Now page ranks have a different interpretation, and departure time delays and between planes going between airports, and and I think the actual graphs and images are hidden here because they kind of break some things. Let's see if it's still here. We removed everything, right, Don, because of the Git book issues. Yeah. So anyway, if you click this play button, sorry, not that play button. Remember, you have to click this. A lot of people are forgetting. Maybe I have to put I guess I should put a title cell here saying, whatever, show title, play before going down, right? Because remember, this is just the hidden, play is this button, right? So because this has all the hidden stuff. So if you didn't hit this and then graphs don't work for you, then that's just why. Because I could just leave it like this, but whatever. Okay, that's exercise. So you get graph frames really under your belt on a much more realistic data set. So today, we're going to get into scalable geospatial computing. I have no idea why this happens on this markdown cells. Some weird Databricks bug. Sorry about that. So let's quickly watch this. This is our introduction to Magellan. This is kind of how I got into Magellan. So of course, there's a lot of libraries I'll mention later. So let's listen to Ram's talk from 2016, I believe.
First of all, it's great to be here at the Spark Summit.
Okay, by the way, I did show AJ, like Anthony Joseph, the Chancellor's Professor of UC Berkeley, and then I showed Amit Talwarkar, and then I'm showing this. They're all brown purely by coincidence, and nothing to do with this, right? Seriously.
Thanks for giving me the opportunity to present today. It's been really exciting to see Spark come along this far in this short span of time. And of course, being in New York is awesome, except it's February and it's cold, and I didn't realize that. I used to live here, but having been in San Francisco, California for 4.5 years now, even this weather is too cold. But that said, it's great to be here. So I'm Ram. I'm the architect for Spark and Data Science at Hortonworks. I'm also Apache Spark PMC member and committer. Prior to Hortonworks, I was the principal research scientist at Yahoo Research, where I used to work on basically large-scale machine learning. Some of the problems that I worked on were login risk detection, like how do you detect when somebody logs into Yahoo servers that they are who they say they are. Sponsored search click prediction, so based on what you're searching on yahoo.com or Bing search and so on, what ads should we show you? Advertising effectiveness models, and the general area that I worked in is called online learning. So today I'm going to be talking about something called Magellan. It's a software that I open sourced over the last few months. So I'm going to be talking about, I've actually given a talk explaining Magellan at the previous Spark Summit in Amsterdam. So I'm going to avoid talking too much details about Magellan at an introductory level. I will still quickly go through what Magellan does and why I'm excited about it and why I think people should be excited about it. But let me still set the framework and the context for you a little bit. So basically, the problem that we're trying to solve is geospatial analytics, right? And geospatial analytics is any type of analytics that uses spatial structure and spatial context for processing, right? So I've picked 3 use cases here. These are just 3 examples. There's tons and tons of use cases that people encounter. And after the talk, I'd be happy to discuss more use cases, or if you can come up with a new use case that you might want to. But let's say, take an example as Uber, right? So Uber collects mobile data about passengers, about trips, and so on. And if you're Uber, you're likely interested in things like, how does the pickup and drop off neighborhood hotspots change with time, right? So sometimes it's Soma that's the hotspot for pickups and drop-offs in San Francisco. Sometimes it's actually a different region, different neighborhood in San Francisco, and this changes with time. So a problem like this is basically a spatio-temporal analytics problem. And this is an example of a business intelligence query that uses geospatial context. So the context that uses here is basically your mobile data. Somebody has to figure out, given latitude and longitude, what neighborhood of San Francisco or what neighborhood of New York is it, and then use it in an aggregate query or something. Second problem is, this is fairly canonical for railroad companies or transportation companies and so on. So you collect GPS data, so mobile data is basically GPS coordinates, and GPS coordinates have a certain accuracy limitation on them. But let's say that you are a railroad company and you actually have very, very fine measurements about the railroad tracks. What I've shown here is a very smooth curve. Obviously, the real world data is not that smooth. But let's say you have data about the railroad tracks at a feet level, then can you actually correct these GPS errors? So the idea here is, can you correct GPS errors with more accurate landmark measurements? Now, obviously, to do this, you have to understand what is actually going on this path. If it's a train moving at a uniform velocity, it's easier to correct that. If that's not the case, it's a more complex problem. But in either case, problems like this involve looking at points, mapping them to the closest grid, and figuring out what the point is that lays on the grid that's closest to this point is. So it's like an example of a near neighbor query. The third piece of it, which is kind of the original problem that I started looking at for geospatial context, is search advertising. Right? So I have an example here where somebody types in Canyon on Google search, and you notice that there's a few things that pop up. Now there is some ranking algorithm that goes and figures out, what do you mean here? Do you really mean Canyon Hotel, for example, or do you mean Grand Canyon, or do you mean Canyon Ranch, and so on? Now actually I did this query in Google yesterday, and I was in New York at this time. Now Google Canyon Road, New York City shows up as a kind of fourth option here, and Canyon Ranch is actually in Texas. So I was really not looking for Canyon Ranch, right? So somehow your search engine should do a better job of knowing where you are and figuring out what query is actually, when you type a partial query, what are you really trying to get at? This is actually not an easy problem, right? In essence, you have to incorporate location as a component, as a feature in your information retrieval, and going further, it's a feature in your search engine advertising problem. So these are 3 canonical examples of geospatial analytics. Okay, so that said, while I'm going to describe what Magellan does and why is it so cool, the first question that I have to answer is, do we really need one more library to do this, right? Anyone who's done geospatial analytics before has used a variety of libraries. Actually, there's probably no single library you would have used, but you would have used tons and tons of them to do some spatial analytics problem. So that in itself is the first problem, which is there is really no one library that you can use today that does geospatial analytics at scale and solves 2 problems, which is simplicity and scalability, right? You want the library to be simple to use, so you can specify the problem that you're trying to solve, but you want the library to take care of scale for you, right? So if you sacrifice simplicity to achieve scalability, that's going to slow you down in terms of development. And the combination of this is actually hard. So it's actually really cool that I'm giving this presentation here because this is the problem that Spark solves for you in the first place, right? So the reason why Spark is so popular is because you don't have to give up on simplicity to achieve scalability. Okay? And that's also the reason why Magellan is written on top of Spark, as I will get into. The other piece of it is a lot of geospatial libraries do exist at some, if you trade off on simplicity or scalability and so on, but then they don't handle some things really well. So for example, when I give you neighborhoods or when I give you kind of roads and so on, the road is just a geometry. The neighborhood is like a polygonal geometry, right? The context that's attached to that, like metadata, is what describes what is this geometry about, right? Is it a neighborhood or is it something else, right? Is it a lake or a neighborhood, right? Now, metadata is not really handled well in most geospatial libraries that I know of. Right? The other piece of it is indexing. So most data formats that exist today for storing geospatial data have not really thought through how to index this data so that we can make scalable queries. Right? And the last piece of it is the storage itself is not very efficient. So today, anyone using Hadoop, for example, or Spark, knows that you can leverage columnar storage to accelerate queries as well. But none of the data formats that exist today and are canonical for geospatial actually have efficient columnar storage. The other piece of it is, so geospatial is not just BI, right? It's not simple business queries anymore. You're starting to ask statistical questions, you're starting to ask machine learning questions. Like I quickly described, the search advertising problem uses geospatial data as a component of a machine learning pipeline. When you do that, you want your library to not be a bottleneck, meaning just to do geospatial analysis and add a geospatial feature for machine learning, you shouldn't have to take the data, move it to some other system, run your queries there, and get back the aggregated data set and continue with your processing. So one of the goals of writing Magellan was to make this whole thing seamless. Right? And lastly, well, this is actually the time to write such a library. So there is a lot of explosion of mobile data. So there's actually a lot of point and space data that we collect today. There is also a very fine granularity of data collection, even for geographic data. Right? So, for example, roads or neighborhoods and so on, we are collecting data at a much finer grain. Right? So, it makes the combination of, when you have a combination of explosion of mobile data and combination of geometries that are, have a lot of data points in them, this really becomes a big data problem. The other piece of it is the analytics actually stretches the limits of traditional view. Right? So there is room for much richer algorithms, there is room for much richer scalable analytics here. And the last piece is, this is the time to do it, and there's also the time where somebody can actually do it in a sensible way, because Spark SQL, Catalyst, and Tungsten already exist, and they go a long way in making the scalability problem simpler for us to handle, right? And I'll go through that in more detail. So today, now is really the first time that we've had an open source engine that's this powerful as a SQL engine, and it's not just as a SQL engine, as an engine that allows you to extend SQL. So for all these reasons, this is the right time to do this. So very quickly, I'll introduce Magellan. So basically, what we're going to be talking about for the rest of the talk is geometric data.
This is the lecture.
Geometric data can essentially be thought of as points, polygons, and polygons. Points are easy. They are, when I talk about two-dimensional points, you can think of them as a triple of two doubles, right? Polygons basically can have holes in them, or they cannot have holes in them, right? So this is a polygon which doesn't have holes in them, and the way Magellan represents this polygon is the array of indices has size 1. There's a typo there, that should be a size 1 array, and the array of values has size which is the length of the number of vertices, right? So for example, this one has vertices 0, 0, 1, 0, 2, 0, sorry, 2, 1, 1, 1, and so on. So the way it is represented, it's represented making a counterclockwise term. That's just convention. You could represent it using clockwise term as well. And if you have holes in this geometry, then you basically have to tell Magellan, or Magellan has to tell you where the contours start, right? So the outer contour starts at at index 0, the inner contour starts at index 5, and then you have a list of vertices. So it's a fairly tight representation as far as representing the data structure itself goes. Now, how about reading data, right? So if you're familiar with geospatial data, there's a bunch of formats for storing this data. Two of the most common formats are called shapefiles and GeoJSONs. So let's assume that you have the New York City neighborhood map stored in either shapefile format or GeoJSON format. What we allow you to do is we allow you to read this as a data frame in Spark SQL, right? So the code that you will write to read this is basically you will help the SQL context that you're using Magellan as the data source, and then you will give it a path to load the data from. Now, if you have to load GeoJSON, you'll just tell us that the option, the data type is actually GeoJSON. Either way, what you get is basically logically a table. The table has two columns in this case because it's neighborhood data. It's a polygon and it has some metadata. Metadata is represented as a map. Right? In this case, metadata has basically the neighborhood and the value is Marina because this is San Francisco. Cool. So that's as far as rating data goes. What about queries, right? So here's an example query in measurement. Okay? So you have some data that you've already read. You may have cached it or you may not have cached it. Now, once you have this data, which is represented as a data frame called neighborhoods, what you can do is you can ask for all the polygons, all the neighborhoods that contain a given point, right? Now, obviously, there's only one neighborhood that's not contain a given point, or at most one neighborhood that's not contain a given point. In this case, it turns out that that point happens to be a North Beach. So the result of this filter is going to give you a new data frame, which has exactly one neighborhood, right? So the thing to notice here is that it's expressing the query is super simple, right? It's if you're familiar with Spark SQL, this is just very much Spark SQL. The only difference is that we have like a SQL extension that allows you to kind of define things like shape literals. So given a longitude and latitude, point of longitude from a latitude gives you an expression that's a literal, right? Similarly, we have a within operator, which basically is a binary expression. It's a Boolean expression. It takes two things, basically two shapes, and figures out whether one shape is within the other, and so on. So that's as far as kind of queries, simple queries go. What about joins? So let's say you may have a table of neighborhoods, and you may have a table of trips, and you may want to say, well, each trip gives me basically latitude and longitude, and I want to know what neighborhood does this point lie in. Essentially, what you're doing there at that point of time is a join, right? And joins are easy to describe here. Basically, it's as simple as what you would say in English, like points.join neighborhoods, where point is within polygon, right? Super simple. And the result of that is basically gives you point, polygon, and metadata as the new data. Right? Okay. And you can also do near neighbor queries, for example. If you think about it, a near neighbor query is basically equivalent to saying that instead of looking for polygons that are close to a given point, I can basically buffer the point by a certain distance, create a geometric object out of it, and look for every other polygon that intersects the object. So it's the same problem. Right? So essentially, near neighbor query boils down to the previous step. So if I can solve intersects or contains or within operators efficiently, I can do near neighbor queries efficiently. Okay? So very quickly, if I am doing point within polygon, for example, so given a point and given a polygon, I want to know whether a point lies within a polygon or not. That's one of the algorithms that do this is a geometric algorithm. Actually, all algorithms that do this are geometric algorithms. One of the geometric algorithms is the following, right? So if you notice, if I take a point and just draw a ray going to infinity vertically from each of the 3 points that I have represented here, 2 of the points are inside the polygon, 1 of the points is outside the polygon. The ray that shoots from the point that's outside the polygon meets the polygon in an even number of points, right? Whereas the ray that kind of does this for points inside the polygon meets it in an odd number of points. This, in essence, is the algorithm that Magellan employs, or any other esri or any of the geometric libraries out there employ for figuring out whether a point is within the polygon or not. The key problem with this is, of course, that it's an order k algorithm, right? If you have k edges, it basically takes order k time to figure out whether a point is within the polygon. You can do better if so in this case the polygon had some weird edges and so on, but if the polygon was what's called convex, you could have done this faster. You could have done this in order log k. But a lot of polygons we see in real life are not going to be convex. Okay, so that said, going back to the join that I was just describing to you, one piece of the join is given a point and a polygon, figuring out whether the point is within the polygon. We just saw an algorithm to do that. But the other piece of it is given a data frame of points and a data frame of polygons, figuring out for each point what polygon is contained, or what polygon contains this point. So that's a join, right? Now, today, what does Magellan do? Because Magellan is written on top of Spark SQL, we really didn't have to write a new join algorithm at this stage. Even without doing any more work, we already inherit all the join algorithms that Spark provides. And in this case, if the neighborhood table is small enough, it's just broadcasted to every node, and essentially you do a streaming read of the bigger table and do a broadcast Cartesian join. It's a Cartesian join because there is no primary key. If the neighborhood table is not small enough, then you end up with a regular prediction. So that's the state of affairs right now. Okay, so that's a very quick look at measurement. So what is its status? 1.0.3 has been out for a couple of months. It's written in Scala. There is Python code there also, but it's not fully functional yet because it needs to be upgraded to Spark 1.6 for that. Currently, it runs on Spark 1.4. It's available as a measurement Spark package called measurement. It's on GitHub. We blogged about it. There's a Zeppelin notebook example as well. It supports 3 of the most common spatial data formats: the esri files, GeoJSON, and OSXML. So the biggest takeaway I want you to take out of this is go try it out. If you have any kind of geospatial analytics you want to do, go give it a try and shoot me feedback about it. I'm always happy to hear about it. Constructive criticism as well as exact. Okay, so that said, what I'm going to be talking about for the next 12 minutes is what comes next. What comes next in measurement is Spark 1.6 support, of course, and that's also the point in time where you will see Python support coming. The 2 things I'm going to talk about today are spatial joins and persistent indices, but we also want to leverage constant better. Today morning you heard the talk from Nangli about optimizations coming into constant.
So our library has all of these features. So ours is only one we call.
So going forward, the biggest problem that we want to solve in measurement next is scaling the Cartesian join, right? So the problem with Cartesian join is that every point has to go to basically has to, until I look at all polygons, I don't know whether a point is contained within a polygon or not. And the point within polygon algorithm is complex. So there is a time complexity involved here, which is actually a problem, right? So the biggest problem you see at this point in time is I told you that you're working on a scalable engine for geospatial analytics, but there's a limit to what we can scale to, right? So yes, I'm also grumpy like that cat. Now, but it's not, it's a solvable problem. So the question is, how do you solve this problem, right? What do you need to do at this point is figure out the first logical thing to ask is, should I send every point to every partition? In fact, do I need to? Secondly, within each partition, do I need to look at every point and look at every neighborhood to figure out whether this point lies within the neighborhood or not? Clearly, we are doing a lot of work today, but is this work necessary? Right? You actually don't need it because one part of this problem is geometries that kind of rarely change, right? So basically, they are either neighborhoods in San Francisco, neighborhoods in New York City, their roadways, waterways, whatever it is. Those geometries change, but they don't change that often. So you can easily index those geometries, and if you can find the right way to index them, then lookups is not going to be that hard, right? So you convert this problem into a pre-processing followed by a faster query processing problem, right? So once you start thinking about indices, there are very many indexing techniques that you can look at. Some of them are quad trees, R trees. There's also dimensional reduction. In dimensional reduction, I'll quickly talk about space-filling curves. So basically, what happens in dimensional reduction is, instead of looking at 2-dimensional indices, you want to look at 1-dimensional indices, right? Somehow convert the 2-dimensional problem to a 1-dimensional problem. Now to do that, I need a 1-dimensional reduction which preserves nearness. So if 2 points are near in the 2-dimensional space, I want them to be near in the 1-dimensional projection as well. And I want to somehow enable range queries, right? One of the nice things about 1-dimensional indices, like what B trees provide for you is range queries. And in the case of approximate reduction, for example, I want to have as-2 collision. So the first way you could have done this is break up your space, in this case a small square, into a few pixels, and then just do a row order cursor, right? So in this case, I can start numbering from 0 and say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I sum 8 are the points. So the square on the left will be 0.0, the square on the bottom right will be 0.8. But the problem with doing this is that the squares, the leftmost square and the square that's right below it differ by the number of, differ by the dimension of the horizontal space, right? And that can be arbitrarily large. So it violates the property that 2 points that are near to each other in the 2-dimensional space end up being too far from each other in the 1-dimensional rotation. Same problem with the snake order curve as well. What happens to work is something called a z-order curve, and a z-order curve is, as we have seen here. The nice thing about a z-order curve is there's a recursive definition of z-order curve, right? So this curve actually, if you keep doing this recursive construction all the way through, it's going to start filling the space completely, right? It's what's called a space-filling curve. So with the z-order curve, you can actually put a binary representation of it. In this case, you can think of the leftmost top left corner as 0, 0, bottom right as 0, 1, 1. So traversing the z-order representation is like going higher than binary representation. The nice thing about it is, if I now recursively define this at 2 more levels, I get this representation. So the nice property here is that everything that starts with 0, 0 is within the first square that I described. Right? So it has a nice containment property. So the properties are locality, 2 points differing by 1 bit, for example, are close to each other. It's got containment as a property. It's very efficient to construct. If I know the x and y coordinates of a point, I can give you the binary representation right away, and vice versa. And it's got some nice bounds on how accurate this is. And if you're familiar with geohashing at all, geohashing is basically z-order curves, where you take the binary representation and convert it to a 32-bit base, 30-bit encoded speed. So I'm going to skip a bit about geohashing and stuff like that. So once we have this kind of a scalable, this kind of a way of constructing spatial indices, how do you speed up joins? The way you speed up joins is you pre-process the points. For each point, figure out the geohash or the spatial index associated with it. For each neighborhood, you won't have a unique index or a unique geohash. You're going to have a collection of them. So on the one hand, you have a single geohash for a point. A particular shape will be covered by one or more geohashes. And then you can just do inner join by the geohash, right? So when you do inner join and geohash, you're now not sending every point to every partition. So this actually speeds up the computation quite a bit. There's a little bit of an edge case here because the squares that cover the geometry have a certain position. So even though a point and a polygon may share a geohash, it doesn't mean the point is within the polygon. It could happen that they just share the same box, right? So there are edge cases that you have to deal with, but you won't have too many edge cases if the polygons are fill the space well. Okay, so that's basically the upshot. So essentially, Magellan 1.0.4 is working on spatial joins, and spatial joins solve this problem of being able to laterally scale these kind of joins. And in SparkSQL, because SparkSQL is written in an extensible manner, it's very easy for us to plug in all these algorithms right into SparkSQL. What we do is basically define a new strategy called a spatial join strategy. The strategy decides whether it's even worth it to do this join in this manner, right? There are some scenarios where it's just too much work to do this, and it's faster to just do a broadcast addition join. In that case, we just fall back to the canonical join. Otherwise, we handle this ourselves, and we override the binary node to figure out how the physical execution plan should look like. And then we stitch it up together as an experimental strategy in SparkSQL. So that's basically a quick description of what Magellan does and where we're going next. And the big problem that we're trying to solve is spatial joins, which should make scalable geospatial queries happen. Not only happen, but happen under the covers without you having to worry about it. The nice thing about it is when we release 1.0.4, because of the way it's written on top of SparkSQL, we add a new spatial join strategy, and everybody who's using the previous version of Magellan already gets this enhanced join. So you don't really have to kind of worry about these kind of joins and so on. The framework takes care of this one, right? Again, this is possible because we kind of hijacked SparkSQL to do this. So it wasn't too much work on our side. So basically, the simple answer here is the join implementation was too slow. We leveraged spatial indices, which is a construct in geometric algorithms, and Catalyst, which is a property of Spark SQL, to fix this one. Okay. So I think I'm going to end with this basically. My Twitter handle and GitHub coordinates are here. So feel free to reach out to me if you have any more questions about Magellan. I think that's it.
Cool. Thanks very much. We've got about 4 minutes for questions, so raise your hand and I will run to you to ask the question.
All right. I'm not going to say much more. I mean, I'm kind of giving you a lesson on how I learned this, right? So this is basically, so I actually watched the 2015 one as well, because we were using the older versions of Magellan when I was working at this company in R&D and sort of try to keep up with Magellan. So this is already a couple years old, and so let's just sort of get into this. This is, I showed you these Microsoft papers already. I'll put links to them later on. And I just sort of talked about this earlier. What we're going to do is this. So this will again happen, right? We currently have been just going to Maven coordinates, doing some search, and just loading some Java archive file. But then if you do that now, it's not going to work because Magellan jar is old in Spark package. And so anyway, what we're going to do now is this. Just download this locally, throw it into your laptop. So you can just go there and hit the download button on GitHub. Right. Like this. Yeah, it just comes down directly. And then so then what we're going to do is load that that jar into yeah. So you would go here and then go to your shared area, I guess, and you would say create library. Okay, but now the default is upload, so you just drop the jar here, right? Whatever you downloaded, just drop it there. I'm not going to redo this because I already have it and attached to the cluster. So it should be like this, Magellan Assembly 1.06 snapshot jar. Right? And then go to the notebook and hit the detach and reattach button. So your notebook picks up the... So... okay, so also I don't want this to be a black box, so I'm not a software engineer, but but I don't want too many mysteries. So if you go to Scalable Data Science, well, this is happening. I'll quickly tell you, we have something called custom builds, and then in there are jars. So then yeah, there's something called assembly and snapshot, but assembly is what we want because it has all this stuff bundled up. And there's a README there. It sort of tells you to build bleeding edge Magellan that is not in Maven. Okay, so you need Git, of course, so you can clone Ram's repo. That's this Magellan Git repo. So then you have the freshest stuff, and then you cd into that directory. And then there is this command, vim. Well, okay, I use the text editor vim, but whatever, you can open it in some editor, and you look at build.sbt, and then you have to change this Hadoop version from 2.7.3 to 2.7.0 for some other reasons, because that's what Spark is using upstairs for us. And then you just do SBT. SBT is simple build tool. It's, I know some of you know all about SBT, but it's another command, and it'll automatically take the sources and assemble a huge Java archive file for you with all the dependencies bundled in one place. So for example, it is calling is it the Environmental Sciences Research Institute? ESRI? Yeah, so it's actually calling commercially friendly licensed low-level libraries within Esri, like esri-geometry API and things like this. So it's really not redoing anything that needs to be. Okay, that's just in case you need to do this on your own later, which can easily happen. Okay, so as you see, we have a lot of these jars we'll be mucking around with today. So then we basically go back here, and if you hit this detach and reattach button, everything should kind of magically work. Okay, so we'll see. So okay, that's 2016. This is the more recent blog. Kind of read about a bit more details. This is just Ram's blog. Yeah. So this catalyst optimizer I briefly mentioned, that's in maybe the second most important Spark paper. After the RDD paper is the SQL and catalyst engine paper. And we will not get into this New York City taxi dataset for reasons that have to do with this dataset is not that exciting because it only has this drop-off points and pick-up points. But the Uber example he talks about from 2015 has a lot more rich structure. It's got the ID of the Uber and timestamp. It's much more richer, closer to John's problem, so we'll use that. But anyway, this is basically And then one of my students, Victor Ingman from last semester, did took 50 minutes and repeated Ram's analysis on this data. So that's a notebook here, I think. So this is basically what he's talking about. I forgot the name of this theorem. Do you know this, Eric? What is this? This? Huh? No, there is a theorem. You know, this whole odd and even intersection. Do you know the name? Doesn't matter. So some famous. It's a. Huh? I don't know. It's a low-level theorem, right? It's like this Euler thing where he jumps around bridges and, you know. Yeah, so it's a you know. So pure maths is kind of important. You want to Uber ride. You should be happy some clever people thought about random things. So anyway, I won't go into all this, but just knock yourself out and read about the blog in more detail if you like. Yeah, this is just a summary of Ram's talk. Okay, so what I've sort of put all the sources I've been using to chelate this notebook. So this is various Databricks notebooks and whatever I pilferage things from, but it's all there. Yeah, so this is basically stuff Marina did, you know, from her talk. She added some slides, so you know about points and polylines and polygons, and the predicates we'll be really getting into are just within and intersects. We're just points within polygons is quite powerful already for a lot of things we want to do. And then we have, so this is how we get started. So we say create a points data frame. And I'm just creating a RDD and converting it to a data frame with X and Y labels. And then, so now what I'm doing is, see, I'm importing Magellan.point. So that's a thingamabob. So that's a point class in Magellan. And then I want my user-defined function. So this is like a sort of one standard way of creating a new column in your data frame. So then I define this thing called two-point user-defined function, and it's simply UDF, which is my built-in thing, and I can specify what comes in, which is X and Y, which are doubles, and then it returns this Magellan point object, okay, point XY. So it takes just a pair of doubles and converts it into a Magellan point, and it's kind of a handy thing to have around because I can't just throw X and Y, a pair of doubles, into things if I wanted to have the properties of instances of Magellan points. So the other way to do it is this. This is just two-point UDF, or to create this data frame. So the new column, you just call this user-defined function, and you get XY converted into a Magellan point. Okay. So now this is so now you import Spark SQL Magellan DSL expressions. So remember, Spark SQL is written in an overridable manner, so you can override on top of the Spark SQL's Catalyst engine, right? At a high level, what is it doing? It's figuring out your logical plan for your query, optimizing the logical plan, and then finding out a physical plan to execute on the infrastructure, and then optimize the physical plan and execute, right? So there's a lot of heuristics and the various strategies you can implement. That's what Ram was talking about, right? He has his own geospatial strategy that he uses to override the underlying default Catalyst strategies, where, you know, sometimes. So in that sense, it's supposed to be quite clever. So it's very thinly sitting on Catalyst and Spark. You know, I was going to present like these other guys as well, like GeoTrellis and GeoMesa, who actually have a lot of value, especially if you're doing bulk ingestions, because they're sitting on top of NSAs like Cumulo, on top of HDFS. It has a lot of value. But then, you know, I saw this most recent talk by Ram where he shows these numbers that sort of blew me away. I don't know if that slide is here. So he shows these numbers where, you know, these are simple queries for these simple points within polygons or contains queries. It beats both the single machine system and the multi-machine systems of all the different open source competitors. So I kind of said, okay. And also, I don't have time, right? I mean, so the syntax sucks, right? Because you have to battle the syntax. If you get anything out of this course, I'm just helping you go through this way faster than it would if I weren't doing this. I can guarantee that. It's a lot of pain. And we should really all thank Dylan because he's done something to fix it before he went to bed in New Zealand. So the other notebook that's coming at you. And you know, the sad thing is these things will change. So if I teach this in 3 months, it's going to be someone's fingertips that's going to burn. So that's why I've completely open sourced this. Like, it's even unlicensed, right? Just if you understand it, do it, and then I'll merge back your fork because we'll all save time and energy basically. Anyway, so this is my, unfortunately right now display doesn't work. This is a real pain. So normally you would do display points dot within columns, and so the data frame notebook that I shared upstairs, that instance of the Databricks display layer, which is sitting on top of another whole Databricks environment used to work, but now it doesn't. It gives you bogus answers. But I just put images of what it should look normally. But we'll just use .show for now and kind of believe what we put in is what's really there. So some display bugs. So what I've done now is generate a sequence of pairs of random numbers. Don't make this too big, it'll crash your machine. So I'm just showing you 10 for this example. So just the next double gives me a uniform number in 0, 1, a pseudo-random string. And I'm just multiplying it by -1 and 1, right? So I'm just getting numbers uniformly distributed between -1 and 1. And yeah, I don't know, I'm slightly, oh well, let's try this. This number may crash your thing, so maybe drop it. So I don't know, this is, maybe it'll crash mine. So this is not a good way to test it, right? Because he was basically saying, this particular way of using point UDFs is better than, or slower than this other way, whatever. So I was just testing it, and sometimes it was good, sometimes it was bad, but then I realized that this way of testing is actually terrible because I'm just creating a huge sequence of pairs of numbers in the driver program, and that's the bulk of the time, and then I'm kind of converting it to an RDB. So I think a more appropriate way to test this would be to actually have some kind of, maybe write this simulation into a Parquet file and then read that Parquet file using both ways. That's a more, okay, if you want to do competitions, and I don't know if I did it for you. There's some computer science people asking about timings and stuff the other day. A lot of computer science guys are into like how fast my algorithm is. So anyway, this is just I didn't really, yeah. But yeah, I also crashed my cluster trying to do this, so maybe we should skip this. So it's supposed to be faster, not using UDFs. So this is again the same blog that is from before in SQL when we went to Spark SQL. So I really fully don't understand the details of all this memory management with tungsten. It's like way too much electrical engineering for me. But anyway, they're doing some low hardware level optimizations as well with this tungsten layer. So okay, these are various links into Jaskowski's page on these details. Whole stage code gen, and what are all these things these guys are talking about. And so if you want to drop in, those are the links I would chase. Yeah, I'm not sure what this was, I forgot. So this is some benchmarking. Oh yeah, this is yeah, actually some benchmarks for this tungsten thing. Okay, now let's just start going through these slides that Ram had, right? He defined polygons and blah, blah, blah. So this is how you would do it. You would import a Magellan polygon, and you would do this first thing where you create a case class called polygon example, and this case class, I hope Dylan isn't doing something on the other notebook here. So anyway, I may not execute all the cells, they should work. So the case class basically tells you, what the type is going to be. Yeah, I told you. So for me, this would normally work, but I think Dylan is probably running this Google protocol buffers of ingesting the San Francisco's OpenStreetMap in the same shard. So anyway, Well, this is the Garvard. Yeah. Well, anyway, this is. Let's just drop this down. Should work. Yeah. So now this is another. Actually, this is good. So this is a problem that will happen when you either, when your Java garbage collector sort of loses its top, or you just overloaded the driver memory and crash your JVM, whatever, and other reasons. Your driver can just die. So that's okay. So all you have to do is, you can do many things. One thing is you can just restart the cluster. Oh, right. Yeah, so I'm going to just restart the cluster, okay? For me, a lot of other things are happening as well. It's a tiny cluster. So. But you guys executed those numbers fine for your simulations? You converted to a data frame fine? Okay, that's good. Yeah?
I have a problem for command 15.
Oh, no, so you have not loaded the library correctly. So if you say Java lang no such method error, it usually means or the Spark cluster you started is 2.3 and it's not 2.2.0 like I wanted you to have for these 2 days. So let's find out what yours are. Yeah, so yeah, if you're running 2.3.0, so yeah, just restart the cluster with 2.2.0 and Scala to 11. So for these 2 days, yesterday and today, we want, this was, Marina will tell you all the amazing pain of not knowing this detail. So Spark cluster 2.2.0, to be safe, 2.2.1 should work, but you're on your own. And then Scala version 2.11. So just create a cluster like this that, for this week, and you can restart it. Because latest Magellan benches against that. And there are changes in 2.2.3, which includes sort of delicate things that the latest Magellan doesn't. Yeah, it's something going on. Okay, so yeah, so let me now try and make sure I import. I mean, these things are good that they're happening, right? Because this is what's going to happen, and you're going to lose your gas because it's sort of annoying. Okay, so yeah. Okay, so let me see. So that's my first import of Magellan, right? So I'm okay. So I think that's where you probably busted. Okay, so I'll just kind of yeah, I'm gonna skip this silly test. It doesn't matter. It's contrived anyway. So yeah, so let's do this. So I'm gonna have a case class, and then I'm simply defining my val ring to be an array of Magellan points, right? So I have 1, 1, 1 minus 1, right? That's 0, 0. So this is 1, 1, and then 1 minus 1. Is that right? And then what? 1 minus 1 minus 1, 1. And then yeah, minus 1, 1. So yeah, so that's basically it. And I don't know exactly if the orientation matters or not. So I mean, I'm going clockwise in the way I've done it, and Ram said the convention is counterclockwise, but it doesn't matter, whatever the convention is. So that's my ring, and then I'm going to create my Magellan polygon by having the first element to be array of 0, because remember, that's the array of the index of the first element. So this is my index 0, index 1, 2, 3. So that's how, like, when you have a polygon within a polygon, then you would say this is index 4 is when this square polygon within that will carry on. But here I just have 1. And then I put my ring with all my information on the points. And so now you can start parallelizing that. And, so what you're parallelizing is a sequence of the polygon example. Remember, this is the case class we defined. And the polygon example simply takes a polygon that we made here, basically. I'm just pumping it directly in here to data frame. So I'm showing you this kind of little example because that's basically kind of the lowest level catch you want to do from some numbers to these Magellan objects. Okay, and if I show false, I don't really see much because it's this weird string thing to the class or whatever the object. So display doesn't work for now, but it should look something like this when it works properly. It'll give you x coordinates, indices, y coordinates. So it'll give you x and y coordinates explicitly. It also calculates all these things automatically for you, like what is the bounding box, the lower corner, -1, 1. This becomes the bounding box. So that's calculated. The bounding box is used, as one of the basic features and some of these other algorithms like spatial joints, because you can use a bounding box of a polygon to quickly do more clever things on spatial queries and stuff. Okay, so predicates, the main predicates we're looking at is points within column, points, and then you take your points and then you use with column to create a new column called point, and there you basically do this, you create a point with the x and y values, and then now you want to join it with polygons, the one upstairs, and then you say where point intersects polygon. This is exactly like from Ram's slide, but with just one polygon and a few points. So now, what are the 3 points that intersect the polygon? So I don't know. So what were the points? I don't know. So -1, 1, -1, 1, and 1, -1. So they all intersect, right? Because they're all on the corners. And I don't know. I forgot what there was some exercise, but my brain is so fried. They didn't have beer at lunch, today. Did you see the? It's I blame the Rulon, So okay. So when you say within, there's nothing, right? I think that's what I'm supposed to do. So because they are on the boundaries, so it has to be a complete subset. I mean, it has to be inside. So let's change this back to intersects. Is that right? Okay. So I think that's enough. These very simple things are enough. These predicates and these geometries for a lot of stuff. And I guess the Magellan's plan is to bring all of Esri into one's disposal in a scalable, simple way. But, so yeah, anyway, a convex set is just, this is a convex set, right? He said if it's convex, it's a lot easier to find containment, and it's just a set where every pair of points within that set, has, whatever, you can get to 2 points in that set by remaining in that set, basically. Anyway, we don't need to get into all these things. And this is just a jog from that slide that he had explaining the odd intersections and the even intersections. So yeah, so So yeah, I just basically, that's the image in this Magellan blog post upstairs. Okay, so now we just made these points and polygons. And let's consider the following points within polygon join query. So this is really kind of a workhorse for lots of things. And we just did it upstairs anyway. So now line is this. So to create a line, you just say import Magellan line, case class line example, and then lowercase line colon type line. This is Magellan line. And then you can just say val line of point comma point. So a line is, 2 points. Specified by 2 points. And then I'm just, turning this into a data frame by using my case class, and I can do lines.show and get a data frame of a line object made of 2 Magellan points. Yeah, display will look like this, and if you look at what's shown, it has bounding boxes, and it calculates a bit more stuff on where the line starts, and so there's some more metadata representation. Now a polyline is just like Marina said, it's just a bunch of lines, many lines, literally. And so that's what you use to represent various shapes. And this doesn't have to come and close back on itself like a polygon. So that's an example. We go from 1, 1, 1, minus 1, minus 1, 1, to minus 1, 1. So again, you can see this. This point is here. We didn't come back to where we were. So the display looks. Here is a polyline with 2 or more lines out of the same ring. Right. First line starts at index 0, and the second one starts at index 2. And yeah, this is just taking the same ring and then saying I just have 2 lines. So polylines are basic primitives for ways in OpenStreetMaps. Okay, so you can do a bit with Magellan and Esri under its hood. I really had this ambitious plan of like getting all the way to Magellan and Esri and coming back like a superhero. It never happened. I'm just human. But I just started off, okay? So, especially like you, who Esri and stuff, you will just know everything. But yeah, it just never happened. But you can look at this, right? Because if you even just want to go and hit this tab button, you're going to hopefully see back from Oregon. Maybe traffic is crazy. You can see what all the stuff is implementable on it, right? So usually you would see a whole bunch of methods. So you can figure out various things. I'm not sure, probably some traffic issue. So, if I can do, for example, take my point P and get the X value or get the Y value. See, these are all implemented methods, and you can drop down here, downstairs directly into the Magellan GitHub repo and look at the source and tests for it. I can also do this type of stuff, right? This is within circles, so this is like very close immediately to a lot of the problems John was saying, for example, or even Marina. I want to know if I take a point as a cafe, and then I can say, here's another point PC. So is that point P within a circle of radius 5 of this other point PC, right? So you can just quickly find, if you have trajectories, you can find all the people that are walking close to your cafe, and then whatever, I don't know. Okay, so yeah, that's true, because 0, 0 is PC, and P is actually some, within 5 units of that. So you can also get the bounding box of a point. What else? Yeah. So if because we have some set valued math people here. What is the bounding box of a point?
Points. Yeah.
That's right. So that's important, right? Yeah, if the point is machine representable, it's that machine representable point. But here, let's really get into this, right? What is the bounding box of a point that is not representable by any floating point number? The point is really here, but the two adjacent floating point numbers next to that point are one oop away, So if I just crash as that point, I will fall through the number screen, right? So that's a non-machine representable point. And, Magellan is not rigorously lyrics, okay? But you can have a machine representable bounding box of that non-machine representable point. And if you start doing things like this, then, this is extremely important. If say the Japanese are mining near-Earth asteroids, they are, with robots. Currently, I don't know of any, any instrumentation specification we can do by international law to ensure that these Japanese near-Earth mining asteroids do not cause a near-Earth extinction event, right? Because I love life, not just my children, but all the fungi, everything, right? It's beautiful. We don't have, forget about social media. That's a very low-level problem to actually. So these kinds of arithmetics are necessary for it. And even other things like exploration, nothing as intense like mining operations, but exploration, right? When you do sailing, we're sailing into space, right? Like our ancestors were sailing into the oceans several hundred years ago. Now, sailing into space, really far corners of space, uses this very, very nice mathematics where you're trying to take the gravitational, what do you call this? The gravitational pulls of multiple bodies, right? Multiple planetary bodies. So it's very important to go to the right point and then give a little kick and just you kind of sail with the gravity, right? I mean, that's how Indians reached Mars faster than Americans, right? They started way late. The most recent, anyway. India's Mars budget, space budget is nothing. It's like a Bollywood movie or two. The movie budget is way bigger. Anyway, don't quote me on that. It seems like that. But anyway, these problems are all extremely sensitive to the instrumentation error, how you propagate that instrumentation error in your machine representable number screens. So in fact, to give a tiny advertisement, so my PhD dissertation was on only focusing on the numerical error and the empirical resolution error of the sensors. And I call this epistemologically valid experiments. So, epistemology is a branch of philosophy, right? That's all about knowing the limits of what you think you know. Epistemologically valid, this is statistical experiments, right? And someone was asking earlier, so only for the numerical limits on, to account for the limits on numerical resolution and limits on empirical resolution of sensors, right? And this is restricted to modern European empiricism. It's the branch of Aristotelian logical schools. Dualism. So anyway, it's not everything, but it's that's what I try to do, in my dissertation. But anyway, I couldn't get a job in the US, which is good. I ended up in New Zealand because that's too esoteric. I was doing some weird statistics. All right, that was a big excursion on bounding boxes. So anyway, Uber trajectories in San Francisco is what we won before Fika, and this is a perfect time. So this is exactly the data from Ram's talk. I think Uber sort of made this data. Yeah. So what we have to do is, load this data, which you won't have, I believe. Did we do this last time? Did we upload this data? TSVN. So then you have to go downstairs. Step 0, downloading data sets and loading into DBFS. So I always put it in the bottom because you just have to do it once per shard. Okay, this is end. Yeah, so let's do this. Oh boy, it's multiple copies. Oh. Yeah, so you should just start here, getting Uber data. So you can, you can try this wget. you know, if it doesn't work, try this. This is like my backup copy in case. So that should be faster because I think GitHub will be. Yeah. So once you grab this all.tsv file, that's your trajectory for the Uber. Then just print working directory. You should be in Databricks driver, but just to check. And then we just make a directory for Magellan. We'll call it dbfs datasets Magellan. Okay, and then yeah, this is, yeah, you can do this or use the %fs copy command, but yeah, this is, so now you're copying it into this Magellan directory. This should work usually. You should see all.tsv in the distributed file store. So then just grab the San Francisco data. So I put the San Francisco data in this zip file in my home domain. It's kind of a lot, right? Or is it 47 megs? Yeah, and unzip it. And remember, these are the files Marina told us about, the SHX and SHP and SPX. It's actually a bunch of files inside a directory. That's the esri shape files. So we will do that because that's usually how government agencies will have their content. And then if you do ls-al at this point, you'll see all.tsv and then all this unzipped planning neighborhoods files, San Francisco. And I think the last step is loading that into the dbfs. So yeah, I'm kind of doing this super slowly. So I make a directory because it's for reasons later. And then I make a directory called San Francisco neighborhood locally. And then I move all my planning_neighborhood files into that directory. So you can just hit this command and then I list all the contents of the San Francisco neighborhood directory. I just threw all the stuff in. It's because the zip file was not already put, all the files weren't already put into a directory. And this again is usually how people will give you zip files. You unzip them and it just spatter in your face. So anyway, so I usually make a temp directory and then put that stuff and let it explode in there. Otherwise you'll be sitting there figuring out what came from where. So yeah, it's kind of what I had to do. So I thought I'll just repeat that for you guys, making it easier. So now I'm making a directory called Magellan. Inside Magellan, I do sfnbhd. And then I'm going to just throw these files, copy each file into that directory. That's basically how Magellan's reader of shapefiles expects it to be. Okay, and yeah, it's literally Control-Enter sequentially. Right, and I don't know how far Dylan got, but we can do all of this in an incredibly beautiful way for Beijing trajectories from Microsoft Research. Except Microsoft Research, at least this morning, they had like 14 zip files of all the Beijing trajectories, and they now only exposed the first one. I don't know why. I should have confiscated it a couple years ago. So, but then when you have the zip file of the trajectories, you don't want to do this. There is a whole different Hadoop file reader method I told you about, where you can directly read zip files using the appropriate Hadoop writer. So we'll use things like that for real large problems. This will be too slow. Is everyone happy with those steps? Okay, great. So then we can go to the very top, and then you should see those files in the right place.
Sorry, this
yeah.
all TSV file, was that also in the same directory?
You have to get that as well, right? You have to fetch the TSV file.
Where I missed that.
So I think that's in step 0. So if you search for step 0, it will take you right above.
Step 0 is.
Yeah, so you control that. Oh yeah, that's 0. So you're getting Uber data. That's the one.
That was the one I missed.
Yeah. Just hit that.
That was
Yeah.
step 0. Okay.
Yeah.
Yeah, I started below. I just didn't
Yeah.
So I missed the first one. Sorry.
Yeah, no, that's cool. So I think, yeah, just follow through and then copy that into the DBFS. Where are we? Okay, so everyone should be here. Right. Oh my God, this is a lot of Marina's markdown embeds everywhere. So that's why it's very big. There's a lot of, it's good. A lot of, so okay, you guys should be here. You should see these two files. I mean, one folder and one file. So now what we're going to do is, yeah, so Marina already told you a bit about shape files, and we can see them. They're there in the DBFS. And then, okay, yeah, there's some watching homework. So if you want to really see this, you know, you can drop back to 2015, and you can watch Swam. I mean, once you get used to the South Indian accent, you can watch him at 1.5x speed quite easily. So I'm basically recreating the 2015 talk here. So which is, this 2016 talk is on New York, and the data is not as interesting. So I create a case class for Uber record, right? Because I want to throw it into a data frame or a data set. So I have something called trip ID, which is a string timestamp. So this is you know, my timestamp, which is going to be a string as well, and my Magellan point, which I'm going to call point. Now, now I'm going to sort of roll this very simple thing. I'm going to create my Uber, which is an immutable. And I'm simply going to use the simplest method. So .text file will read text file from a distributed file store, and you know, it'll automatically break it by end of line characters. So each thing that's coming at me on this map is a line. So I take the line that's coming at me, and look, I'm doing all these things to have all the things I ship between partitions in full closure. So that's why I put val. You know, especially point. For this, I really needed to be declared inside here. So I split my line by tab because it's tab separated variable, and then I define my trip ID to parts of 0 because that's the first thing that comes out. And this is a super clean data set, so we don't have to worry about any regexing and fielding. Parts of 1 is timestamp, and then I take parts of 3, convert it to double, parts of 2, convert to double, because remember the long lat order is always mixed up with X and Y. That's why 3 and 2 are here, and then I make that a Magellan point, and then I use the case class of Uber record and throw in my things I just cooked up, right? Trip ID, timestamp, and point. And out will come an RDD that'll have Uber record, right, which is ready to be data framed or data setted, right? I mean, turned into a data set or data. That's the case class helps with that. And then I cache it, so it's now going to be at least the recipe is made to throw it in distributed memory upon the first action, which is done here. Okay, so how many Uber records? And I think it's over 1 million. So, right, so it took 9.15 seconds, and of course, if I rerun it, it should take a lot less, okay? 0.44, because it's going from the cached RDD after the first action. So there are over 1 million Uber records. Then let's read the neighborhoods. So this is the beauty. Now I can do SQL context read format Magellan, right? And I'm just going to load that directory in my distributed file store DBFS with all those files. And then I'm just going to select a few fields because it's got so much stuff in there. I'm just going to select the polygon and the metadata columns. So that's done. So then I'm going to count how many neighborhoods are there in San Francisco. So apparently there are 37 neighborhoods. That's from the official San Francisco County. So it's the official
This last query, why are we using SQL context instead of Spark context?
Well, okay, so I mean, basically Spark context is provided for us in Databricks called SC. It's always there, right? But there are also other entryways, something called Spark. Let's not go there. So the usual one is SC. SQL context usually comes from the Spark context, but then once again, in Databricks, the lowercase SQL context is already predefined for you. So SQL context is going to be, just like streaming context is like, I don't want to use the right words here. It's like for a given Spark context, remember we had a streaming context as well, which you had to define, SSC, Spark streaming context, and we started and stopped. But we stopped the Spark streaming context without stopping the Spark context. So these things these contexts run within the basic entry point of the Spark, which is Spark context.
Yeah, but couldn't we have done the filter?
No, because it is an SQL operation, right? This is an SQL reading operation. I'm reading a specific format from Magellan.
Okay.
And when Magellan is integrated with SQL with its own overloaded operators. Yeah. So, I don't know. It's just syntax, but focus on this part, right? So now we get into, actually, the syntax is what kills you, because we're still struggling with the, these other files we want to read. Okay, let's get into neighborhoods and look at the print schema. Because I only pulled a couple things, polygon metadata, I'm only seeing that, but we can play around later if you want with what's really there. So now I'm basically showing just the top two. There is so the metadata looks like a map. It has key value pairs, and the key is neighborhood, and the value is Twin Peaks. So it's like a, I don't know, standard way to do some metadata. Then so I think if I do false, so yeah, this is just a silly example. So you can say so not sleeping. So you can look at all 37 neighborhoods, right? If you don't do anything, the default show will only show 20, I think. So it's Chinatown, and south of Market is Soma. That's what Ram was talking about. It's a very popular destination for trips that start there and end there, or whatever. That's a 2015 talk, I think. So and then now let's do this, because Spark SQL functions has a lot of methods like explode, which is like a different way of playing with. What do you call it? Flat map. When you have one-to-many mapping that comes out, explode allows you to take, say, a data frame with a column that has arrays, and then it just kind of will explode into a whole bunch of columns with each element of the array, for example. So these are not most optimal always, but yeah. But it's fine. So now I'm just basically exploding the metadata and turning it into a column. So I can also specify the column name as a sequence of strings. So this is K and V. This again is very convenient if you explode some metadata that has 800 elements, and then you can specify a sequence of 800 string names, right? So that's good. The neighborhood, and so this join below yields nothing. So this is kind of like this from his 2015 talk. So what's really going on? And well, this is basically going back to Marina's issue. So there is some issue with the native representation of the geographic coordinate system for the Uber guys and the San Francisco guys, right? So all the points are falling in some other part of the world, basically. So I won't go into this. Marina sort of gave you a lot of pointers into it. So we need the right transformer to transform the points into the right coordinate system of the shapefiles, right? So here is the, so we're going to just roll out our custom transformer. It's basically just a grab of the actual code that was there. So if you look at this, this is our transformer. So if you really go here and show code, there's quite a lot going on. This is a case class NAD83. This is North American Datum 83. And you can kind of get into this a little bit. You can define the zones from and to. So there's a full case class class with methods defined for this particular transformation, right? There's well, there's a bit more transfers to Mercator. I just left it there because at one point you kind of maybe want to look into this and maybe if you start your own nation in some island, you know, you can roll out your own coordinates. Or, who knows? Okay, so we have to do this transformation, right? So we just define this transformer, and then it just takes my sort of, creates a new column called nat83, and then it takes my point, that's just the previous column there, and then it hits it with the transform method through the transformer we created, and it's going to cache that. So now I have uber transformed. So now let's count uber transform and make sure we have the same number. So of course the first count will take about 10 seconds, 4 seconds. And then uber transformed, if I just show what's there, I can see that, you know, ooh, what happened? Oh yeah, here. So yeah, I can see the new column, right? And these numbers are very different. So this is in meters, right? We're going from degrees to meters, is that?
No, I think it's with the specific 983.
Yeah, it's a wrong one.
Not 83, there are some in meters, some in feet, it depends which
Okay,
one you
oh, okay,
choose.
yeah. I don't know what this is. Yeah. It's in some metric scale, so let's quickly go for Fika, because I want to. So, okay, uber transform select trip ID, distinct, count, gives me the number of unique trip IDs. No magic, right? Just there's 24,999 Uber trip IDs. Of course, they could be the same Uber driver, but the trip ID itself is like where it starts and where it ends, I believe. Yeah, I think so. So then here we have joined. So here let's try to join again after the appropriate transformation of the coordinate system. So this should be okay, so now let's look at how many Uber records are in the neighborhoods, right? So I just did a join, and this will be a broadcast hash join, I think. I don't know what's, yeah, probably. It's too small. I'm not sure really what's going on, so it could be one of the more fancier methods because this is the latest Magellan. And if you want, you can ask the data frame to be explained, I think. Dot explain, is it? I forgot. So there's some syntax you can do, and then it'll give you the full. Is it explain? Do you guys remember? Yeah, I forgot. You know, there's a way to look at. Oh, that's the count. So I want the join dot explain. I think Control C. Do you guys remember when? Yeah, so it gives you the physical plan and you know what's in memory to, I don't know. Okay, you can just jump into this some more software engineering guys, you know, like, I don't know. Don't ask me, I'm tired. Just read it if you want, but it's not really necessary. So, you know, this is basically what I'm doing, just showing you the top 5, and I'm seeing that this trip ID 1 at this timestamp is in this neighborhood. Same trip ID at the immediate next timestamp is in the same neighborhood, and so on. So, of course, here's records not in the neighborhood shapefile. So whatever is defined to be San Francisco by the government, there are trip IDs that leave San Francisco, which makes sense. They're probably going to another airport or who knows what, to the neighboring county. That's okay. It's important to be aware of it. Now we just do a group by neighborhoods, and then we aggregate the distinct trip IDs as trips, and then we order by the column trips in descending order and show. So this gives me the trips that are in south of Market, Soma, Western. So I'm sort of showing you the most popular neighborhoods that the trip IDs fall in, right? The distinct trip IDs fall in. Okay, so I think this is this is basically what Ram covered in his video. I don't know, it says Ross to do deeper dive into Magellan points with polygon queries. Yeah, forget it. I'm not going to do anything more. That's enough, okay? So this gives you guys enough gas to go as far as you want, basically. So after the Fika, what did Dylan tell me to do? So Magellan OpenStreetMap ingestion. So I think, yeah, let's try Uber map matching. I think one of these things work, so we'll figure out. something, but let's have fika. Are there any questions?